Okay, folks, it's time for our next online lecture. Today we're going to talk about magnetic energy, displacement current. We're going to fix Amperes Law. It has a little thing we need to add. And we're going to briefly derive Maxwell's equations in matter. So let's begin just by remembering what we did last time. Last time we were talking about how if we have a loop of flux, then we were talking about how if we have some flux in that loop, defined as simply the B field that penetrates the loop, integrated over the loop, then we see that there's an EMF which develops in the loop if the magnetic flux is changing. So we were talking about EMF and how that develops if I have a changing flux. So we know that. And then we were talking about this in terms of inductance. So for the inductance, we were relating this to the concept of inductance. For example, if I have an object, then I know that the self-inductance is L. If the self-inductance is L, then the flux through that object is the self-inductance L times the current that flows through it. So this is just for a very simple system. If I have some current, and then I can have some B field here for this type of situation, in which case the EMF can be written as EMF is now can be written in terms of the inductance L times di dt, since that's just the change, the negative change in flux. Okay, so these are the things that we were talking about last time, but now we want to expand on these concepts, and we want to talk about, we want to answer this new question, very important question, and it's an energy question, and the idea is, the question is, how much work does it take to create a magnetic field? That's the question. How much work to create a B field? Now, this is also, we can rephrase this question, because another way of asking this question is another way of asking the same question is to say, if we have some self-inductance L, then how much energy to ramp up the current? Then how much work to ramp up the current? And that's perhaps a better way of thinking about it, at least initially, because that's what we do actually in a laboratory. For example, here's the situation I'm talking about. Let's create some loop. There's my loop, and now if I'm passing current through it, then the current is flowing like this. And basically we want to know how much energy does it take to create this kind of situation. Now, and let's suppose that there's no dissipation. So let's ignore resistance. Let's assume that the wire has no resistance for now. And so this might actually seem like a silly question, but it's not, because what happens is, as we increase the current, we create a magnetic field. And you can see the magnetic field using the right-hand rule. The magnetic field grows in this loop. That's the magnetic field. And so you can see then that as we ramp up the magnetic field, then we're going to be changing the flux. As we ramp up the current, we'll be creating that magnetic field, and we'll be changing the flux. but if we change the flux, then you know what's going to happen. The d phi b dt changes, and that creates an EMF. Then EMF develops. And what happens is the current has to fight against the EMF. It has to fight the EMF. And that's the energy that we expand to create the current. So whenever we want to, if we ever have a loop and want to ramp up the current, then it's going to cost us some energy because we have to push the current against the EMF. And so a way to see this is to think about, for example, if I put some current, it goes into the loop in this direction, then some current is going to be coming out of the loop in this direction, right? Because current is conserved, and that charge is going to have to, that charge that goes in and out will have to go around the whole loop, and then I'll have some E induced, some induced electric field, and the charge will have to go against that electric field. And so what we can see then is that the work to push that charge against that induced field, the work done by an outside force like PG&E that you have to pay for is going to be it's going to be negative times the force on the loop on the charge times a little bit of distance that it has the charge has to go around the whole loop, I got to do that integral around the whole loop, the current loop. So that's the work that takes an outside that's the work that takes an outside some outsider to put to an outside agent to push charge around that loop. Now you know that the force that is felt by the charge in the loop is going to be that force will simply be the electric field, the induced electric field inside. Let's see, that's the force on the delta Q. And so then we can see that the work done by the outside agent, that was the word I was looking for, agent, is going to be equal to, I got to put the Q here. So that's force times electric field times, force is equal to electric field times Q. And so the work done by the outside agent is going to end up being negative dq times the integral over the loop E dot dl. And so what we can then do is first we can notice that this is the EMF, E, the EMF. And so then we see that the work done by the outside agent is simply simply negative delta Q times the EMF. And so that kind of makes sense because that's just energy is equal to charge times a voltage, because EMF is like a voltage. And so what we can do then is, what we can do next is now we can divide by time, by delta t. So we're going to assume that we can push the charge through the loop in some time delta t, and so then what we have is that we'll divide both sides of the equation by delta t, and so the work done by the outside agent per time is equal to, here I have negative, and here instead of delta q I'll call it dq dt times the integral E dot dl. Where this is just, of course, the EMF, and so this then is equal to negative I times the EMF. And so then what we can do is, we know that the EMF, on the other hand, I can write the EMF as we can write the EMF as negative L di dt. And so what we have then is these negative signs cancel, and so we end up with dw, the time derivative of the work done by the outside agent, is equal to L, I have Li, and then I have di dt. And so then what we can now do is we can just knock off these little dt's. We divided by them, we can get rid of them. And so then we have this simple expression, the little bit of work that it takes to increase the current by a little bit di, it takes, so this is how much work it takes to increase the current by this amount di. And so then we can figure out the entire amount of work to get that, to ramp up the current. I integrate this from 0 to the total amount of work. And then I just have to integrate this from 0 to the total amount of current. And so then that's a pretty simple integral, and we see that the total amount of work is equal to 1/2 times L times the total amount of current squared, just from doing that integral. And of course we don't always write these t's there. We just like to say now that the work is equal to 1/2 Li squared. And so that's the amount of work it takes to ramp up the current through some loop. I'll draw it again. So there's the loop, the current. So to ramp up the current, it takes that much. Even though the wire has no resistance, it takes that much energy, because we have to create this magnetic field in the loop, and we have to fight against the EMF, and that's why it costs us that much energy. And I want to, and you know how I always like to look back on the electrostatics formulas that we've derived, and I just want you to see how it looks like the electrostatic formula that we derive for capacitors. It looks like the electrostatic expression for capacitors, because there's a real strong analogy between electrostatics and magnetostatics. And so for capacitors, we have U is equal to 1/2 Q squared over C. And so now we have U is equal to 1/2 Li squared. And so we can see that we have the same role here for 1 over C has the same role as now we have for L, and Q plays the same role as now does current. So I just want you to see that analogy. So this is the energy basically of an inductor to ramp up the current in an inductor, and it should remind you of the energy it takes to charge up a capacitor. It's the same kind of idea. Now the question we can ask is, where is the energy stored? Where is the energy stored? Because the energy's not lost, because there's no dissipation, and so it's not like the energy is lost, and we put that energy into the system to ramp up that current. So where is that energy? Good question. Where did it go? And you know the answer already, probably from some other class. It's stored in the B field. That's where it is. The energy is stored in the magnetic field. But how does that work? Let's and what's the expression for how can I relate the energy to the B field? Let's do that. So let's derive an expression that let's do the math, and let's derive an expression that relates energy to magnetic field. We want to relate the energy to the magnetic field of a current loop. Okay, so how do we do that? Well, we just start with the expression that we just derived. It's actually a cute little derivation. It's one of my favorite little derivations because it's pretty straightforward. You just consider the energy of a current loop, like the one I drew above, there's some inductance to the loop, and it has current flowing through it. And now let's just rewrite this expression, because I can rewrite it in a very simple way. I can rewrite it as 1/2 times I Li. So I just broke the I squared into I times I. No big deal. But now I have L times I. And what's the inductance times the current? Well, by definition, that is the magnetic flux through the loop. And so this is then 1/2 I times the magnetic flux in my current loop. But magnetic flux, we know, is an integral. So I can rewrite this as 1/2 I times the integral of B dot dA. So I'm kind of making taking basically a simple formula and making it more complicated. And this is a surface integral over area of a membrane of the loop. And so now what we can do is we can still rewrite this, because now we know that B is equal to del cross A. So we assume that there's a vector potential. There always is. And so now we can write it in terms of the vector potential. So we have here the integral over area of del cross A dot dA. But of course, you know what happens if I integrate a curl over the area of a membrane. We can then use Stokes Theorem. That's what we always do. We always do it. Stokes Theorem. So let's do Stokes Theorem, and so that means then we can write the energy to ramp up the current in that inductor is going to be 1/2 I, and now I'll use Stokes Theorem on this, and Stokes Theorem on that is just going to give me the line integral of the current loop, A dot dl. Over the current, or now this is a line integral over the boundary of the loop. Now what I can do is I can bring this. I can bring this I in here, and I can rewrite this as 1/2 times the integral of A. Now I can say dot I, the vector, times dl, the scalar, where I'm basically taking the direction unit vector out of the dl, and I put it into the I. So this is something we've done before, so that's not too complicated. So now let's remember something from a long time ago, not that long ago, but let's remember that I dl is equal to J d tau, where this is the volume element, the differential volume. And you guys remember how we did that, because we just what we see is that this is easy to derive, because you remember that I is just equal to J times dA, and so then we have dA times dl, and dA times dl is d tau, and so I dl equals J d tau. All right, so it's like current times a little differential length is equal to current density times a little differential volume. So now let's change this integral, and we can see now that we can rewrite this integral by saying that the work it takes to ramp up the current in that loop is equal to 1/2 the integral of A dot. Now instead of IDL, I'm going to replace that with J d tau. And so this is a volume integral. And so this is an important expression for energy. So that's the energy of that's the energy of a system of current loops, or a system of current distribution. Energy to create a current distribution. And once again, this should look familiar to you. It should look sort of familiar to you because I love to do this. It looks a lot like the electrostatic case because for the electrostatic case, remember, we were asking what's the energy to create a distribution of charges, and we derived this formula that the work is equal to 1/2 times the integral of how did I write it before? We would just say 1/2 times the potential. Whoops. Or I could just say V, the electrostatic potential, times rho, the charge density, d tau. And so I just want you to see how we have the same formula here, but now I have, instead of a vector potential A, we've replaced the scalar potential with a vector potential, and we've replaced the charge density, or the charge density is now replaced by a current density. But I want you to see how it's the same type of expression. Okay, so that's the magnetic energy. So we'll call this magnetic energy, because that energy really is the energy that it takes to create the magnetic field for the current distribution. But we still don't see the magnetic field yet. We got the A in there, but we still haven't got the magnetic field. So let's get the magnetic field in there. But before we do that, let's consider a more general situation. Because what we've been talking about so far is just a current loop. So for example, I could have this inductor. So this is a nice simple inductor, and so this is what we've been talking about. Although this is several current loops, but it's the same thing. You can just multiply by the number of current loops. But now let's make it more general, because now let's put some magnetic material in there. So now we have some magnetic material with the magnetization, because that's what a magnetic material is. It's described by some magnetization vector, right? Vector field, which is, remember, magnetization is the dipole moment per volume. That's what magnetization is. And so let's put some magnetic material into that into that inductor, as I've drawn in this picture. And now we can ask, what is the energy to ramp up the current for this situation, where I have not only a loop but some magnetic material nearby? Now the thing is, it's really the same. It's the same expression, but just a little. It should remind you of what we did already for the electrostatic case, because we have this same expression, but now we have to realize that the J here is not all the J's, because remember, J total is equal to J bound plus J free. But when you turn on the current from in your power supply, which is plugged into the wall, the current that's coming out of your power supply is this, J free, not J bound. J bound is in the material. So the work that you're actually paying for to ramp up that current, this is only the free part, J free. But the vector potential, that's where the material can come in, because this vector potential here is the total vector potential, which arises from not only the current, but the material also, everything. So that would be J free plus J bound. So this is the vector potential for everything. So this is the expression for the work to ramp up the current in that inductor. And so now let's work with this expression. And the first thing to remember is that now we can start getting the fields in there, because we know that J free, if I have some free current density, then we know that that's going to create curl in the H field. H as in Harry. So that's our J free. And so now we can see that our work to ramp up the current in this situation, in that inductor, is going to be the vector potential total dotted into del cross H, integrated over volume, over all volume. And so what we want to do now is we want to massage this into a more convenient form, and to do that we're going to use a vector identity. Use a calculus vector identity. This is one of those identities that you find on the cover of your book that you guys have hopefully derived in some previous class, maybe even this class for the homework. And so this is the identity that we want to use. Let's use this one. Del dot, and this is a general identity. Del dot A cross H is equal to H times dotted into del cross A minus A dotted into del cross H. All right, so that's just a calculus vector identity, but then we can notice some things. For example, we notice that here we have del cross A, and that's B. That's the B field. And so then what we can do is we can write, we can pull this over to the other side, and then we can pull this over to the other side, and then what we'll get is what we'll get is A dotted into del cross H is equal to H dot B minus del dot A cross H. Okay, so that's just a little vector identity that we derived, but now that we've derived it, we can plug it in because we see that this is the same as this. And so now we can, so what we'll do is we're gonna replace this with this in this equation. So now we see that the work to ramp up the current is 1/2, but now it'll be times the integral of this mess, which is H dot B minus del dot A cross H. And that's integrated, remember, over volume. And so this is quite nice because then we can write those two integrals separately. It's going to be 1/2 H dot B d tau minus 1/2 integral of del dot A cross H and d tau. And now we're going to do a little trick that we've done before. We're going to notice that that's an integral of a divergence. So we're going to use Gauss's theorem. And you guys all remember that. That's our favorite little theorem. That's just telling us that the integral of a divergence over a volume is equal to the same thing, -1/2, but it's going to be the integral of that vector field as a flux integral, dot dA, over the surface. So we've turned a volume integral of the divergence into a flux integral. And we've done this many times, so hopefully that should look pretty familiar to you. And so what we do next is we realize that we can now take the limit as the surface goes to infinity, because that doesn't change anything in this integral. We can always take the surface as it goes to infinity because all the derivation we did so far doesn't depend on the size of the surface that we're integrating. So we'll take the surface to infinity, and then we see that the integral of A dot A cross H dot dA is going to equal 0. I guess you could guess it because these things go to 0 at infinity, because the limit of A and H as the surface goes to infinity is equal to 0. So that means that we can that means that the second integral is we can cross it off. It goes to 0, and so that means that the work to ramp the current up into our loop is 1/2 times the integral over, now it's over all space. We have to be very careful. It's over all of space of H dot B d tau. And so so now we can see that the work is stored in the B field, and then that's it. So this is a very general expression, quite general, but then for a linear material, it gets a little simpler, and most materials are linear, so it's an important case. But for a linear material, then what we see is that for the linear material, we have H is equal to B over mu, where mu is the permeability. Mu equals permeability. And so that then tells us that the work is equal to 1/2 the integral over all space of 1 over mu. It'll be basically 1 over 2 mu, because I put 1 over mu there, times the integral of B squared d tau. And so what that tells us then is that there's an energy density in space, and the magnetic energy density is equal to 1 over 2 mu B squared. And that's a very important result. That's the magnetic density. So that's the energy density. It's the magnetic energy density. So that's the energy stored in magnetic field. It's the energy, and we can call this U sub M, and we can say that U sub M is equal to the energy stored. That's the energy per volume stored in a magnetic field. And it's equal to, of course, 1 over 2 mu B squared. And this should look familiar, because it should look very familiar to, I will just remind you of the electrostatic case. It should remind you of that, because we know from the electrostatic case that there's energy stored in an electric field too. So for the electrostatic case, we had we had the electrostatic energy, and so now I should determine. I should distinguish magnetic energy from electrostatic energy. But for the electrostatic case, we have the electrostatic energy is equal to epsilon over 2 times the integral of E squared d tau. And then that led us to the electrostatic energy density, which is, of course, epsilon over 2 times E squared. So they're very similar. So it should look kind of the same. It should look very familiar to you. Let's make this nicer. Epsilon. Okay. And so all right. So that's the energy stored in the magnetic field, and I do want you to see that. You can see how as the mu gets bigger, then the energy it takes less energy to create a magnetic field B, and that makes sense because the permeability is helping the magnetic field to be generated. And so what we can do now is we can so now what we can do is let's write Maxwell's equations, what we have so far. Let's sort of review. So this is like a little bit of review. Let's remind ourselves of what Maxwell's equations look like up to now. Maxwell's equations. And so we see that for free, let's look at them for free current, and free charge density. And we'll add the materials in later, but let's just take a look at them. And so what we have now is we've looked at del dot E. We know that we have the divergence of the electric field is 1 over epsilon naught rho total. That's the Gauss's law. I don't actually have to even write the total part. Let's just get rid of that. So this is, we call this Gauss's law. And the second one is the equivalent Gauss's law for magnetic field is 0 del, because there is no magnetic monopole, so we'll call this the no monopole law. No monopoles. The no monopole law. And then the third one, that's the divergence for the two fields. So now we have to talk about the curl. So let's start with the curl for the electric field. And so we can see that the thing that causes curl in electric field is changing magnetic fields. We derive that. And so if I have curl in an electric field, then I must have a changing magnetic field and vice versa. And so this is, of course, called Faraday's law. Faraday's law. And then the last one is the curl in the magnetic field. So del cross B is equal to mu naught J. And this is Amperes law. Okay, so those are the four Maxwell's equations, basically just the divergence and curl of E and B. That is what Maxwell's equations are. But when we notice this, is we notice that it turns out that they are incomplete. Maxwell's equations are incomplete as we've drawn them, as we've written them. Incomplete. Oh no. Why are they incomplete? It's easy to see. There's two. It's easy to see. Easy to see. Because, for example, there's two different ways of seeing it. Two very famous arguments. Let's consider the first argument. Let's take, if I have Amperes law, del cross B equals mu naught J, then what I can do is I can take the divergence of both sides. Look, check it out. Del dot, del dot. Why not? Del dot. I can do it. And so let's do it. And so this, if Amperes law is true, then so must this equation be true. But del dot del cross B, we know what that equals. That always equals 0. So that's an identity. That always is 0. And so now we have we see that we have 0 is equal to mu naught del dot J. But from the continuity equation, we know that mu naught del dot J is equal to negative d rho dt from the continuity equation. So this is the continuity equation, which is really just another way of expressing conservation of charge. Conservation of charge. But this then is telling us that d rho dt is 0. And so what we get then is that we see that d rho dt is 0. Now this works for steady state. So for steady state, then it's okay. But if it's not steady state, then it's not okay. Not steady state, then not okay. So we see that for dynamic situations, we need something more. For dynamic cases, and dynamic just means d rho dt does not equal 0, then we need something more. need something more. Because the equation we just used led to d rho dt equals 0. But if d rho dt does not equal 0, then obviously that's not true, and so then the equation doesn't work, it's incomplete. So that's one way of seeing that Amperes law is incomplete. So we can see that, Amperes law is obviously incomplete. Amperes law is incomplete. And there's another famous argument for this as well, I'll just mention, because it's sort of a famous thing that everyone should see at least once in their life. Maybe most of you have already seen it somewhere, but some of you probably haven't. So let's take a look at it. So now let's take a look at let's look at it now from the point of view of the integral form. The integral form of Amperes law. And the integral form is this. If we just integrate it, we have the integral of, we have del cross B equals mu naught J, and so we just integrate both sides, but we integrate both sides over a membrane, dA, and we integrate it over a membrane, a two-dimensional membrane, J dot dA, and so this is then, of course, the current enclosed, the current that penetrates. We call it the current enclosed, but it's really the current that the current that penetrates the I that penetrates the membrane, penetrates membrane. And of course I have the integral of del cross B dot dA. We can then do the Stokes Theorem and we get B dot dl. Okay, so you guys all know this formula, but now let's apply this formula to a circuit, a certain kind of circuit. So let's have a battery, and let's have a capacitor, and let's do an interesting little thought experiment. Let's hook it all together in our minds. Have a resistor here, and then here I'll have a switch. So suppose I have a switch here, and then I close the switch, close at t equals 0. So I go click and close that switch. Then of course you know what's going to happen is I'm going to get some current will flow after I close the switch. So current will flow, and there'll be, and this is some resistor, and let's just say this is some capacitor, and this is some battery voltage. And so you guys know that current will flow to charge up that capacitor. So while current flows, then we know then that while I does not equal 0, then B must not equal to 0. So there must be some magnetic field around this circuit when that current is flowing. So what is that? So then the question is, what is B? What is the magnetic field around this circuit? So let's do Amperes law. So let's do it right here. I'll do a little loop, a current loop, and I need the area, the membrane area, and I need the loop. So I need the loop, and I need the area, the membrane, so I can do the current flux integral and the magnetic field loop integral. So here's my membrane. So I'll do a loop around the circuit up here, and that's my membrane, and I'll call that A1, the area of that membrane A1. And then we'll do Amperes law. So in your mind, do Amperes law, and you get some, and obviously there's some current enclosed because the current is flowing through that loop. And that's going to give me the B at the periphery of the loop. But here's the trick. What if I chose a different membrane? I could just as easily have chosen this membrane. And I'll draw the lines like this. It looks like the cap of a chef's cap. It always reminds me of like a parachute or a chef's cap. And so I could have an alternative membrane that I'll call A2. Maybe I'll do that. And I'll call this A2. And so if I do, so the point is that if we do, if A1 is chosen, then we have that the I enclosed does not equal 0. But if if we chose the second membrane, then we see then that I enclosed equals 0. So we get a different I enclosed, and so that means how the heck then how the hell can we do integral b dot dl is equal to mu naught I enclosed, because we see now that the I enclosed depends on our choice of membrane, even for the same current loop. So this is really bad. But it turns out that there's a way to fix it, because this is just another way of saying basically that this is just another way of saying that Amperes Law is incomplete. Del cross B equals mu naught J is incomplete. And so let's fix it. So then we have to fix it. Then must fix it. And it's pretty easy to fix it. We have to fix Amperes Law. And so so to fix it, we'll do this. We'll assume that some J, or we'll assume that some chi vector field exists such that del cross B is equal to mu naught J plus chi. But then the question is, what's chi? Well, to find chi, let's do something really simple. Let's just take the divergence of both sides of this equation. So let's take let's do del dot of both sides. And so then what we get is del dot del cross B is equal to mu naught del dot J plus del dot chi. And then what we'll do, but now we know that del dot del cross B has to equal 0, because del dot del cross any vector field is 0. So this thing equals 0. But then what we'll do is we'll notice also that the continuity equation is always true if there's conservation of charge. So we have mu naught. Here we'll have negative d rho dt plus del dot chi equals 0. But then we'll do a little trick. Very simple trick is we'll just remember that rho. We'll just remember that rho, the charge density, is equal to epsilon naught del dot E, because charge density is related to divergence in electric field. And so then we'll plug that in to this equation up here, and we'll get 0 is equal to del dot chi minus mu naught d dt of epsilon naught del dot E. But of course we can just arrange these because these operators are interchangeable, the del and the ddt, they commute. And so then what we have is, I'll write it like this, we have del dot chi is equal to, I'll pull the epsilon out and the mu naught out, and I'll have, I'll write it like this, del dot, del, and then I'll write it as del dot mu naught epsilon naught dE dt. And so then we see that if del dot chi equals del dot this, then of course chi must equal mu naught epsilon naught dE dt. And so we have just derived this new current, essentially. It's a new current. And so what we can do then is now we see that this is what we need. This is what fixes Amperes law. This is the fix. That's the fix. And so now we see the new Amperes law is that to get the new Amperes law that works under all circumstances, or most circumstances, we're still going to be one other thing we'll add in a little bit, but we now have the new Amperes law is del cross B is equal to mu naught J plus mu naught epsilon naught dE dt. And so this is the new Amperes law that we have derived. But there's a nice way of writing it, because the way we like to write it is we like to pull out the mu naught and write it like J plus epsilon naught dE dt. Because now you can see that this must play the role of some kind of current, because it must have the same units as current. It has to for this equation to hold. And so this is some new type of current. And so what we call it is, we call it the displacement current. So this is what we call the displacement current density, J displacement. So J displacement is equal to epsilon naught dE dt. So if you have a changing electric field, then that behaves like a current. It behaves like a current. And what it does then, what does a current do? It creates a B field. So that tells us that a changing electric field has to create a B field, because we see it. This dE dt has to creates curl in the B field. And so this then is is how we complete Amperes law. So we have del cross B is equal to mu naught J, the normal current, which is, I'll just call that's normally J free plus J bound. That's the normal J. But now we have to add on a new one, which is epsilon naught dE dt, which we'll call JD for displacement. And now you can see how this fixes Amperes law for that funny situation that I had before, where I had the battery and I had the capacitor, and I said that there was a switch and a resistor and a switch like that, and the switch came down. Then I got some current, R, V, C, and now I'm going to get some current, I, and then we made that loop. Remember, we made that loop here. And then we were worried about what happens if we make this loop out like that, like a parachute. And now we see that it works, because now I have an electric field that behaves like the current. And so there is a non-zero electric field, and you could even calculate it. It's not too hard. You could even calculate it. Whoops. You could even calculate it, and it's a homework problem. E displacement. So you get an electric field which, well, that's actually the displacement current. So I'll call that the J displacement, which of course is equal to epsilon naught dE dt. And you can see that the current indeed is charging, so as the current flows into the capacitor, the electric field does indeed change with time, and that then is how the Amperes Law can still work. And this is a homework problem to analyze this situation. Okay, so now we see that the Maxwell's equations are better. They're much better, but they're almost complete. So we've made some improvements. So let's write them down now. Maxwell's equations. We fixed them up. They're almost complete. And so what's the situation as we have now is that we see that we have del dot E is equal to 1 over epsilon naught rho, and we have the del cross E is equal to negative dB dt. So far so good. And we have the del dot B. That one is always 0 because there's no monopoles. And then we have the del cross B is now fixed up, is equal to mu naught J plus mu naught epsilon naught dE dt. And you might think that that's totally complete, where this is now, this J is J free, like our normal current, but it also has, bound current can also be in there. And this, of course, is our new displacement current. But it turns out that there's still one thing that we're missing. It's almost complete, but we're still missing one thing, because, and you can see that. The way to see it is, but the problem is still missing one thing, still missing something, still missing one thing. Oh man, what is it? What could it be? Well, it's pretty easy to see if you just look at, let's consider the charge and current. Charge and current. And for charge, we have rho equals charge density, we know is the free charge density plus the bound charge density. And we know that current, J, is equal to, now we have 3 currents. J free, which we know what it is. We can think of that as what happens when the free charge density is moving with some velocity. So rho free times velocity is J free, and we have the bound current density, and we see that that's equal to del cross M. We derived that a while back. That's the bound current density, and now we have this new one, the displacement current density. And we know what that is. That's equal to epsilon naught dE dt when the electric field changes. So what could we possibly be missing? Well, when you look inside of these currents, here, we can ask the question, what about the bound charge? What about rho B? Does that create a current also? Because we noticed that the free charge density creates a current. We notice that the free charge density creates a current. We notice that the magnetization creates a current. We notice that the electric field creates a current. But what about the bound? What about the bound charge? Could that create a current? And the bound charge, we know what it's equal to. It's equal to negative del dot P, where that's the polarization. Where P, remember, is equal to electric dipole moment per volume. Electric dipole moment per volume. And can this bound charge density create a current? Because what about, for example, could I make a bound current where I take the bound charge density and just multiply it by a velocity, the way we did here for the free current? Just saying that J equals rho v. That's what we normally do. Now, of course, that this is problematic because the bound charge is not free; it's bound, so it can't just move with some velocity freely. There's no steady state velocity. No steady state velocity for rho b because it's bound. Damn it. That's the whole point. That's what it means to be bound. You can't move. It's bound. That means it can't just be running away with some velocity. But you know that even if something is bound, like a dog, you take a dog and you put him on his leash, he's bound. And you tie him up to a pole and he's bound. So does he move? Does he have velocity? Of course he has velocity. The dog is jumping around. He's going back and forth. He's pacing impatiently. That dog is moving all over the place. And so we know that there's no steady state velocity, but there is an instantaneous velocity. No steady state v, but there is an instantaneous velocity. Instantaneous velocity. Because the bound charge can be bouncing around like a dog. A dog is bound by a leash to a pole, and it's bound, but it can still bounce around. And the same thing with charge. Think of charge like a little dog, bound by a leash. So here's some bound charge. It's bound to this pole, and it's bound by a spring. I can think of this. So this is bound charge. Bound charge. That's how we think of it. It's stuck to something by a spring, but it can still move back and forth. So it can still have some velocity. And that means that that means that we do get a polarization current. There is a polarization current from bound charge. And so what is that polarization current? Well, first let's just look at it intuitively. It's very easy to see intuitively because here's another way of seeing it, is that if I look at a material that has some polarization, where the polarization is the dipole moment per volume, then if a material is polarized, has some polarization, then this is what it looks like. It has dipoles in it. And here are the dipoles. And those dipoles have some plus charge and some minus charge, right? These are dipoles. And I can think of this really as two interpenetrating lattices. I can think of it as really my plus charges and I can think of it as sort of coexisting with my negative charges, where here's my negative charges. And so if I think of the positive charge and the negative charge on separate lattices, then I can pull them apart. So if I increase, so if P increases, then that's simply the same as pulling these apart. Then same as pulling these lattices apart. That's the same as pulling these apart. Because if I pull this one to the left and I pull the positive one to the left and the negative one to the right, that's increasing. You can see how that's increasing the size of my dipole moment, because this is a small dipole moment and then this is a big dipole moment. If I pull them apart, I get a bigger dipole moment, because dipole moment is simply equal to Q times D, where this distance is D. And so if I pull it apart, I'm increasing the dipole moment. But if I'm increasing, but then again, if I'm doing this though, then you can see that this, if the positive charges are going to the left, then that's a current going to the left. But if the negative charges are going to the right, that's also the same as a current to the left. So we can see that when we pull apart the dipole, that pulling apart the dipole, so we can say that pulling apart a dipole is the equivalent to current. So making a dipole, but the thing is, you can't really pull a dipole all the way apart, but what you can do is you can make the dipole oscillate. So you can make it go bigger and smaller. And so it can oscillate. And so that means that the current as a function of time can go plus and minus. So the bound current, the polarization current can oscillate. It can change in time. All right. Well, so that's just to sort of make you believe that there could be a polarization current, but now let's actually derive it. It's really easy to derive. So derive an expression for it. So far we've just been talking about it intuitively, or at least I hope that was somewhat intuitive. Although I know that everyone's intuition can be quite different. Something that's intuitive to one guy might not be intuitive to the next, but that's my best try at being intuitive. So let's derive an expression for the polarization current. And here we go. It's really easy because we'll start with the continuity equation. Because the continuity equation is just del dot JP. So if there is a polarization current, then it has to satisfy the continuity equation. And the continuity equation says that del dot JP is equal to negative d rho dt. It's negative time. The divergence of the polarization current density has to equal the negative time rate of change of the bound charge density. That's just the continuity equation. And so now that we have the continuity equation, the rest is simple, because we can just notice that the bound charge is equal to negative del dot p, the polarization, the negative of the divergence of the polarization. Now these signs cancel, and then what I can do is I can bring the gradient out, and so that's equal to del dot d dt of p, the polarization. So I see that I have del dot jb is equal to del dot dp dt, and so that means that these things got to be equal. They got to be equal. So that means that my polarization. Oh, I keep changing the name of it. I'm sorry. Let me stay consistent. This is my polarization current, and so J sub P is equal to d dt P. So if there's a time rate of change of polarization, then that's equal to the polarization current. They're exactly equal. And so that means then that now the total current density is equal to, not only do we have J free, but we also have J bound, the magnetic J bound, but we also have the J displacement, but now we have a polarization current density as well. And so J free is just going to be rho free times velocity J bound is going to be the magnetic one, del cross M. J displacement is going to be epsilon naught dE dt. And then the polarization is just going to be dP dt. Okay, so those are our total current density. And now that each of those currents can create a magnetic field. So that means then that the magnetic field, when I write the Amperes Law, that we have to take into account now all of these currents. We have del cross B, because all of these currents create curl in the magnetic field. And so del cross B has to be mu naught times J free plus J bound plus JD plus JP. Okay, so that's Amperes Law. So Amperes Law has a lot of stuff in it. Okay, so now we're finally ready to completely finish Maxwell's equation. So now we're ready to combine everything, combine it all to have the complete Maxwell's equations. We're ready for the complete Maxwell's equations. So this is a very important moment in our lives, to complete Maxwell's equations. It's very exciting, a very exciting moment. And so let's write them down. So now let's combine everything into a nice, compact, beautiful notation. And so let's do it. So let's start with the electric field, del dot E. And so let's start with this Maxwell's equation. Del dot E, the divergence in the electric field, comes from charge density, rho sub t, charge density. But we know it comes from the total charge density. So if we have any charge density, that will create divergence in the electric field. But we know that there's two places the charge density can come from, and that is free charge density, like just some charge that's lying around, but we also can have bound charge density. Bound charge density, and that of course is negative del dot P. But then we can play a little game, and this is a Maxwell's equation, but now what we can do is we can play a little game, and we can move this over to the other side. And so then what we get is we see that we can get del dot E plus 1 over epsilon naught del dot P is equal to rho free divided by epsilon naught. And so then this leads us to del dot E plus P over epsilon naught is equal to rho free divided by epsilon naught. So let's multiply both sides by epsilon naught. And so then we get del dot epsilon naught E plus P is going to equal rho free. But what is this? What's epsilon naught E plus P? What is that? Well, we know what that is. That's the D field. Because D is equal to epsilon naught E plus P. And so that means then our Maxwell's equation is del dot D equals rho free. Okay, and we've seen that one before, but that's the first one. We'll give it a star. And now let's do the second one. The second one is going to be, we took the divergence of the E field. Now let's take the curl. So this is the divergence of E, div E, and now we'll do curl E, div and curl. So curl, the next Maxwell's equations is the curl of the electric field. And what is that? Well, we know it's negative dB dt. That's Faraday's law. We derived that. But the question is there anything else? Plus anything else? Now, here, if we had monopoles, if we had magnetic monopoles, then we would have something else. We would put the current, we would put the electrical current of the magnetic monopoles here, because a flow of magnetic monopoles would create a curl in E in the same way that a flow of electric monopoles creates a curl in B, regular current. But we don't have magnetic monopoles, so there's nothing here. I will just erase it. And so this is, that's all we got. That's all we got for curl of E. And the reason is because there are no magnetic monopoles. No magnetic monopoles. And so as a result, there is no magnetic current. There is no flow of magnetic monopoles. If there was a flow, then that would create curl in the electric field, but there's not. Okay, so that's simple. So we'll give that guy a star. And now let's do the B field. So the first thing we got to do is, let's do the divergence of the B field, div B. And so for the divergence of the B field, we have del dot B. And that one's really easy because that's always 0. That's the easiest one to remember. And of course, it's for the same reason as before, that there's no magnetic monopoles. So that's why I just hope that they don't discover a magnetic monopole until I'm retired, so that I don't have to change all my lectures, because that would be such a pain. Okay, but now let's do curl B, the last one, because that's what Maxwell's equations are. It's just the divergence and curl of the electric and magnetic field. That's all it is. So now we'll do the last one, and this is Amperes Law, and this is del cross B. This is the most complicated one. Well, it's kind of the most fun one. It had the most stuff going on. Got all that current, mu naught. Now, current causes curl in magnetic field. And we have, luckily we have electrical monopoles, otherwise known as charge, electrons and whatnot. And so, and when those things move, we get current, and it creates a magnetic field. But we can get current, but there's different ways in which we can have the current. We can have the free current. We can have the bound current. We can have the polarization current that we just derived a moment ago. And we can have the displacement current, which we also just derived recently, this lecture. And that one is rho, this one is rho free times velocity. This one is del cross M. This one is dp dt. And this one is epsilon naught de dt. And so let's use those. And so that means that we can rewrite del cross B in terms of, we'll write it like this. We'll write it as mu naught JF. And we have the free current plus mu naught del cross M plus mu naught dp, dp dt. Plus mu naught epsilon naught de dt. And what we'll do is we will, we're going to combine these guys, and we're going to pull this guy over to the other side. And so when we do that, what's going to happen is we're going to get del cross, and then what we also want to do is divide everything. Let's also divide everything by mu naught. All right, so then we're going to get del cross B over mu naught minus M from pulling that guy over equals J free plus, and here I have d dt of this epsilon naught E plus P. Right? From these guys. But we know what these things are because B over mu naught minus M has a name. That's otherwise known as H. And epsilon naught E plus P has a name. That's otherwise known as D. The vector field otherwise known as D. And so that means that we have del cross H is equal to J free plus D dt of D, where H is equal to 1 over mu naught B minus M, and D is equal to epsilon naught E plus P. And so this then is our final Maxwell's equation. And so we see, and we'll give this guy a star. So these are our Maxwell's equations. You can see them here. We have del dot D equals rho free, del cross E equals dB, negative dBTT, del dot B equals 0, and the final one is del cross H equals J free plus the time derivative of the D field. Okay, so that's all for today. Thanks. Bye-bye.